Hi, this is Tzvi Rosen. Welcome to another lecture in our online series on matrix theory. In today's lecture, we'll talk about the determinant. This is covered in Chapter 2 of Anton and Rohrs. Let's get started. So what is a determinant? In the most general sense, it's if we have a square matrix A, so if A is equal to a square matrix, then the determinant of A, written as det of A, is a number associated to A. Okay, so that's in the broadest sense. It's a function that takes a matrix and gives back a number. And what does this number describe? Well, one way to think about it is as a volume stretch factor. And so here we need to remember how we treated matrix transformations as mapping one space to another. And some of our matrix transformations were maps from R2 to R2, so maps of the plane. So here's an example. So if we take the plane, and we'll have a little unit vector here, and a little unit vector here. These two unit vectors describe a unit square here, right, whose edges are just translates of those two unit vectors. Now let's consider what happens to this space when we do a matrix transformation. So let's take the matrix to be something simple like 2 and 1/3. Okay. Now what this does is it takes every vector here and it spits out a vector in the plane according to the following rule. So the first unit vector gets scaled by 2. So instead of just a length of 1, we get a length of 2. Whereas the second unit vector gets scaled by 1/3. Okay. And so what we find is that the unit square that we had before got stretched out. It got kind of shorter, but longer in one direction. Shorter in one direction and longer in the other. And you can see if this has area 1, then this is going to have area 2/3 because it got scaled by 2 in one direction and by 1/3 in the other. And so the determinant in this case would be 2/3. Okay, which describes how the area of the unit square was stretched. And in higher dimensions, you would be visualizing higher dimensional volumes. And then the determinant is describing how much those get stretched or squished. Okay. The other thing that's useful about a determinant is that the determinant of a matrix is 0 if and only if A is not invertible or A is singular. That's the other interpretation for this number. It's the number which is 0 when A is not invertible, and it's non-zero in other cases. I'll give a brief example to illustrate why the determinant being 0 corresponds to A not being invertible. So let's consider again this example of the plane. And I'll give an example of a matrix with 0 determinant. That's going to be this matrix, 1, 1, 1, 1. Okay. So when I'm looking at where these two unit vectors map, they're going to map both of them to the vector 1, 1. Okay, so this is here, and this is also here. Okay, so now this lovely blue square, the unit square defined by our two unit vectors, now gets squashed into a line segment. Okay, this has 0 area. Okay, whereas this has area 1. At the same time, this is not going to be invertible because since if I call this E1 and this E2, E1 and E2 map to the vector 1, 1, so there's no way to get an inverse map. A function being invertible means that you have to be able to undo it. But since E1 and E2 are going to the same thing, there's no way I can undo it. I don't know which one to map 1, 1 to. It's either going to map to E1 or E2. It can't map back to both. Okay, so this gives us intuition for what determinants do. They describe how area changes under a linear map, or volume in higher dimensional cases. And when the determinant is 0, the matrix is not invertible. Okay, so let's get started on small examples. So one by one determinant, this is a map from R1 to R1. Okay, if you feed in some real number x, and it gives you a number y, and the way that it works is you just multiply by, okay, so this is x maps to y, and the equation is usually something like y equals kx. Okay? And you can visualize this as living on a line, right, the real number line. Okay, this is the origin, and the way this map is going to work is you're going to feed it some vector x, and then the result is going to be some vector y. Okay, and if we want, we can just keep this to be the unit vector, and then this will be k times the unit vector. Okay? And so if we're describing the determinant as a stretch factor, a volume stretch factor, then this is clearly going to be the determinant of the matrix K is going to be just the number K. Okay. And if the number K is negative, then you'll get a vector pointing in this direction. Because in a sense, the area gets stretched, but also changes sign. So it's not quite an area anymore. Now it's a signed area or a signed length. Okay, but I think we feel comfortable saying that the determinant of a matrix with a single number in it is the number. Okay, now let's think about a 2 by 2 determinant, and we'll think about it one case at a time. So we saw an example of a diagonal matrix. Okay, so the way this acts is that when you plug in E1, which is the vector, so if this is my A, then AE1 is equal to little a times E1. So you stretch the first unit vector by A, and A times E2 is B E2. So you stretch the second unit vector by B. And as we saw in the example I drew earlier, if we have a unit vector here and a unit vector here, then what happens is this becomes stretched, so we end up stretching the green arrow by a factor of a, and we stretch the, okay, so this is now AE1, and we stretch the red arrow by a factor of b, it's BE2, and the resulting area is AB times the original area. Okay. So it makes intuitive sense that the determinant here would be, the determinant of A would be AB. Okay? Now suppose we have an antidiagonal matrix. That's what we call a matrix that looks like this. 0, A, B, 0. A times E1 now is going to be equal to B E2. Okay, so taking in a single unit vector in the x direction, now it turns to be B scaling in the y direction. Okay. Meanwhile, A E2 is going to be A E1. Okay. So how can we interpret this? Well, using the same picture as above, the red and green are going to switch positions. So now the red, when you take this red vector you started with, now it comes down here to be stretched by A. So we have AE1. And then over here, we get BE2. So everything is quite similar to how it was above, but now the green and the red are switched. So in some way, the orientation is backwards. And for that reason, because the order of the red and green arrows is flipped, this gets a value of minus AB. As for a more general matrix, when you have A equals A, B, C, D, here we take our unit vectors, the green and the red, and now these become these get translated to new vectors. Okay, let's say this is AC, or let's write it in column notation. And this might be BD. Okay. Then the signed area of this parallelogram, which is really what we're interested in here, how much is this stretching and is the orientation changing or not? The formula for that ends up being the following. Determinant of A equals AD minus BC. Okay. For all of this stuff, in terms of getting intuition for why these, or rather how these determinants correspond to stretching areas and volumes and such, I would highly recommend viewing the 3 blue 1 brown video about this. It's excellent. I'm going to link to it in the description. But so far, we at least have explicit formulas for the 1x1 determinant and the 2x2 determinant. To go to the 3x3 determinant, we're going to start introducing some new notation. Okay, so for a matrix A, so let's say A is a square matrix, n by n matrix. We're going to define a minor of A to be the following. So we define Mij to be equal to the determinant of the n minus 1 by n minus 1 square matrix, which you get from A by deleting the ith row and the jth column. Okay. That's called the ijth minor, or Mij. The cofactor Cij is very similar to Mij, except you add on a sign. So this becomes minus 1 to the I plus j times m sub ij. Okay, so it's just this extra sign factor. It might just be 1, but it could be minus 1, times the determinant that we defined in the last step about minors. Okay, so let's see how this relates to a specific matrix. So let's say I wanted to compute M1, 2 of this matrix A. So that means I want to compute the determinant of the 2 by 2 matrix I get when I cross out the first row and second column. Okay? So what's left is a 2 by 2 matrix. And that's something I know how to compute the determinant of. So this will be equal to 2 times 1 minus 4 times 0, and that gives us 2. As for C12, that would be given by minus 1 to the 1 plus 2 times M12. Okay, the minus 1 to the 3 is minus 1. M12 is 2, so we're left with minus 2. Okay? Hopefully that's a clear example of a minor and a cofactor. Okay? And that gives us a recursive definition for a determinant. And recursive means you use the small cases to define the larger cases. We define larger cases of determinant using smaller cases. Okay, and it goes as follows. Okay, step 1, fix any row or column of the matrix A. Okay. For example, fix row number 2. Okay. So if we fixed row I, then we say the determinant of A is equal to the sum, where j goes from 1 to n, of Aij, Cij. Okay, so you basically move along the row and you multiply each entry by the corresponding cofactor, and you add those all together. Okay, alternatively, if you fixed column j, then the determinant will be the sum from I equals 1 to n of Aij, Cij. So here you just move along the column, again, multiply an entry by its corresponding cofactor, and add those all together. Okay, if we wanted to think about this in the example where we fix row 2, so in that example, the determinant would be A21 times C21 plus A22 times C22 plus etc. up to A2n times C2n. That would be a formula for the determinant. Okay. That's all pretty abstract using a lot of notation, so let's get this in some concrete examples. Let's do a 3 by 3 determinant. So what we said is we have to fix any row or column. And it didn't tell us which row or column to fix. That's one of the miracles of this definition, is it actually doesn't matter which one you use. So let's just do the top row. So we're going to fix row 1. Okay, so the determinant of our matrix is going to be the sum of the entries times their corresponding cofactors. It'll be the sum from j equals 1 to n, which in this case is 3, because that's a 3 by 3 matrix, of A1j, C1j. For us, that's equal to A11, C11, plus A12, C12, plus A13, C13. So let's compute these cofactors. So for C11, that's going to be equal to -1 to the 1 plus 1 times M11. Okay. M11, as we know, is the matrix, is the determinant of the matrix you get when you omit the first row and first column. So that's going to be -1 squared times, and I don't know if I mentioned this yet, but one notation for determinant is straight lines in place of brackets. So we would put 1, 4, 3, 1. This is the submatrix you get when you omit the first row and first column. And this is, the -1 squared becomes 1, so we can ignore it. And then we're left with 1 times 1 minus 3 times 4. And that is -11. Okay, so that's C11. As for C12, maybe make a bit of room here. Okay, C12 will be -1 to the 1 plus 2 times M12. And that's -1 cubed times the determinant. Now here we're leaving out row 1 and column 2. So we're looking at 2, 4, minus 1, 1. Okay, so again, this corresponds to leaving out this. Okay. And we know the formula for, first of all, this -1 cubed becomes negative. And then we have 2 times 1 minus 4 times -1. And that becomes 2 plus 4, or 6. So we have -6. Okay. And the final cofactor is C13, and that's equal to -1 to the 1 plus 3 times M13. And this -1 to the 4th becomes 1, so it's -1 to the 4th, and that goes away. M13 is what you get when you delete the first row and the third column. So that's 2, 3, 2, 1, minus 1, 3. Okay, and we know the formula for that determinant. That's 6, or 2 times 3 minus 1 times -1. That's going to be 6 plus 1, or 7. Okay, so putting that all together, we have that the determinant of A is equal to A11, which is 1, times C11, which is -11, plus A12, which is -2, times C12, which is -6, plus A13, which is 1, times C13, which is 7. And for our final answer for the determinant, we obtain minus 11 plus 12, because the minuses cancel, plus 7, and that gives us 8. Okay? So that was a determinant computation for a 3x3 matrix. Here's a 4x4 determinant. And this is going to be a little bit choppy, so bear with me. Again, any row or column works, so we can just go across the top. Okay, so we're going to take A11 times C11, etc. So we have C11 is equal to negative 1 to the 1 plus 1 times this determinant, negative 1, 0, 4, negative 1, 3, 1, 2, 0, 1. Okay, then we have C12, which is equal to the matrix you get when you delete first row, second column. So that looks like, well, first we have the sign, which is negative 1 to the 1 plus 2. And we get 2, 0, 0, and 0, 3, 0, 4, 1, 1. And we have C13, which is negative 1 to the 1 plus 3. You know, let's do this over here. Uh, 2, 0, 0, minus 1, 2, 4, 1, 1. And C14 would give us 2, 0, 0, minus 1, 2, 0, 3, 0. Okay. Oh, and I forgot the sign. The sign would give us negative 1 to the 1 plus 4. Okay. So evaluating these determinants using the method we saw on the last slide for 3x3 determinants, we obtain C11 equals minus 27. C12 is equal to minus 6. C13 will be also minus 6, and C14 is going to be minus 12. Okay. Now plugging this into our formula, we have that the determinant of our matrix is 3, that's A11, times minus 27, plus minus 2 times minus 6, plus 1 times minus 6, plus 0 times minus 12. Okay, so that gives us minus 81 plus 12 minus 6, and that's minus 75. Okay, so that's the determinant of this matrix. But we notice something here. We didn't really even need to compute this minus 12 because it was just going to end up getting multiplied by a 0. So it occurs to us that we can choose our row or column so as to maximize the zeros we run into and minimize the number of computations we have to do. So let's see an example of doing that. So in this example, I want to choose a row or column so that I run into as many zeros as possible. So for that, I could pick actually either the first column or the third column. These both have 2 zeros. For simplicity, I'll pick the first column. So in this case, the determinant of our matrix is going to be A11 times C11, plus A12, sorry, this should be A21 because we're in the first column, times C21, and that's it because the other two entries in the column are 0. Okay, so we only have to compute C11 and C21. So C11 in this case is what we get when we omit first row, first column. So that's minus 104, minus 13, and of course we need the sign factor, minus 1 to the 1 plus 1, and 201. And C21 is going to be equal to what we get omitting the second row and first column. So that gives us minus 210, minus 131, 201. Okay. And here, for this determinant, we can also use creative zero choice, right? So I can take this column and compute the determinant along there because it has 2 zeros. So this is just going to be equal to, so minus 1 squared, that's going to be 1. And then this is 3 times, well, we should be careful, this is negative 1 to the 2 plus 2 times 3 times this determinant, minus 1, 4, 2, 1. Okay. And simplifying, so the minus ones go away, and we're left with 3 times minus 1 times 1, minus 2 times 4, which is minus 1 minus 8, or minus 9. This gives us minus 27, which is what we computed for C11 before. How about C21? Well, here it's not as easy. Let's just use the first row. We get at least one 0 there. I just want to move this a bit. Okay. So this is going to be equal to negative 1 to the 1 plus 1 times, so let me write it this way. This is A11 C11 plus A12 times C12, okay, which is negative 2 times negative 1 to the 1 plus 1 times 3101 plus 1 times negative 1 to the 1 plus 2 times negative 1, 2, 1, 1. Okay, that's the subdeterminant. That's the submatrix you get when you compute when you omit the first row and second column. Okay, just gonna make us a bit of a barrier here. Okay. And this gives us, so we have negative 2 times this determinant. You can plug in and get 3, so it's negative 2 times 3, plus this is minus 1 times negative 1 minus 2, or negative 3. So that's minus 2 times 3 plus minus 1 times minus 3, or minus 6 plus positive 3 gives us minus 3. Okay. So putting it all together, we get that the determinant of A is equal to 3 times minus 27 plus 2 times minus 3. This is minus 81 minus 6, which is, oh, not great. Sorry, c to 1, I see the mistake I made. I did not yet include this factor of minus 1 to the 2 plus 1, which would give me a minus sign here. So this actually ends up being, let me mark this in red. So this really should be plus 3. This should be plus 3. And then we get plus 6 here, which gives us minus 75, which is the same answer we got on the previous slide after correcting our mistakes. OK. So what we saw here is that if we choose the row or column to maximize the number of zeros in it, we end up saving a lot of computation time. This strategy is going to be useful for computing the determinants of upper and lower triangular matrices. What's nice here is you can expand the determinant along this column, which means you only have one non-zero entry, and so you only have to worry about one cofactor. But then here you can use the first column, which only has one non-zero entry, and you're left with only this cofactor. And here too, you're only left with, you can use the column with a 0, and you're only left with this cofactor. And so each time, all you pick up is the entry in the upper left corner. And so the determinant of an upper triangular matrix ends up being the product of the diagonal elements. In this example, that's 3 times minus 1 times 4 times 2, which is minus 24. By the same token here, you can expand along here, and then you're left with this cofactor, and you can expand along here to be left with this cofactor. You can expand along here, and you'll be left with this cofactor. And it's exactly the same idea. You're left with these elements. So in this case, the determinant of A would just be equal to the product, which is minus 21. Okay? And so in these upper and lower triangular matrices, the things that are off the diagonal don't actually matter at all. And that's something that we derive using only the cofactor formula for the determinant. Okay. So there's so we've learned how to do Gaussian elimination and get matrices to row echelon form or reduced row echelon form. And the tools we used to do that were row operations. So what we're going to look at now is how row operations affect determinants. Okay, so let's recall what the row operations are. First one is to swap rows. Okay, so let's say that B is obtained from A by swapping row I and row J. Okay, obviously I is not equal to J. Then the determinant of A is equal to the determinant of B, minus the determinant of B. So when you swap those two rows, you pick up a minus sign. And you can get that directly from the cofactor formula, but we won't look at that explicitly. Just keep in mind, swapping rows picks up a minus sign. The next operation that we did is we can scale a row by a constant. Okay, so if B, okay, same deal, is obtained from A by scaling a row by K, then the determinant of B is equal to K times the determinant of A. Okay. Again, this hops right out of the cofactor expansion. You can, if you're expanding along the row that you are scaling by K, every factor picks up term in the sum picks up a factor of k, so you're just multiplying the determinant by k. Okay. And what happens, so what's the third row operation? That's adding a multiple of row I to row j. Okay, and if B is obtained from A in this way, so B obtained from A by adding, etc., then that actually doesn't change the determinant at all. Okay, so again, swapping rows, pick up a minus sign. Scale a row, you multiply the determinant by the scalar. Add a multiple of a row to another row, doesn't change the determinant at all. Cool, so we understand those pretty well. So how can we use that to help us compute the determinant? Well, let's say this is our matrix A. What we're going to do, here's our strategy. I'll write it out in green. First, we're going to put the matrix in row echelon form. And that is going to be, by definition, an upper triangular matrix. Okay, and then once we have an upper triangular matrix, the determinant is really easy. It's just the product of the entries. So the determinant of new matrix is product of diagonal. And then we can use the determinant of the new matrix to derive the determinant of the old matrix. Okay, use new determinant to get the old determinant. Okay, so let's see how this works for A. So we're going to keep track of what we're going to give each of these matrices a new name so that we can keep track of what the determinant is for each one. So let's start by swapping row 1 and row 4 because I want to put, I want this -1 to be in my upper left. So we're going to have A1. So let's say this is our A. Now we have A1. And that's what we get when we switch those two rows. So it's -1, 0, 5, 4, 0, 2, 10, 8, -2, 1, -1, 0, 2, 3, 4, 4. Then we scale A1 by the first row of A1 by -1. Okay, and we get A2. Okay, this is going to be our A2. Okay, and now we have 1, 0, -5, -4. And now to get the first column to be all zeros, we add twice the first row to the third row and -2 times the first row to the third row. And we get A3, which is 1, 0, -5, -4. 0, 2, 10, 8, 0, 1, -11, and minus 8, and 0, 3, 14, and 12. Okay. So now it's useful to switch these two rows, because we've got 1 in the first, to be the leading one in the second row. So we're going to do that. Okay, so at this point we have a 3, and we're going to switch its rows. Okay, and what we get when we do that is a 4. So this will be a 4, and we're going to get, so this will be 0, 1, minus 11, minus 8. So we have 2, 10, 8 down here, and this is going to be 1, minus 11, minus 8. Okay. And now, again, we want to clear that second column, so we get minus 2 times the second row plus the third row, minus 3 times the second row plus the fourth row. And what do we get after that? So we have a5 becomes 1, 0, minus 5, minus 4, 0, 1, minus 11, minus 8. And we have 0, 0, 32, and 16 gives me 24, and 0, 0, 33 gives me 47, and 24, so that's 36. Okay, and now we just multiply this by 1 over 32. Row 3 gives us a6, which will be 1, 0, minus 5, minus 4, 0, 1, minus 11, minus 8, 0, 0, 1, and 24 over 32 is 3/4. Okay, and 0, 0, 47, 36. And our final move is to replace this last row with minus 47, row 3 plus row 4. Okay, and that gives us a 7, which is 1, 0, minus 5, minus 4, 0, 1, minus 11, minus 8, 0, 0, 1, 3/4, and in the final row we have 0, 0, 0, then minus 47 times 3 over 4 is minus 35 3/4 plus 36 gives us 1/4. Lots of cancellation. So at the end of the day, we have the determinant of A7 is equal to the product of the diagonal elements, because it's up triangular now, which is just 1/4. Okay, so now we have to move backwards a little bit. So we have that the determinant of A7 is equal to 1/4. Then how do we get from A6 to A7? We added a multiple of a row, so that's the same. So the determinant of A6 is the same, because adding a multiple of a row does not change the determinant. We scaled A5 by 1 over 32 to get A6. So determinant of A5 is going to be 32 times 1/4, which is 8, right? Because to get 1/4, we had to multiply by 1 over 32. Okay, so then we have A4, that was just adding. So we have determinant of A4 should also be 8 because it was just adding multiples of rows. How did we get from A3 to A4? We swapped rows. So that means that that would have picked up a minus sign. So we have determinant of A3 is minus 8. And A2 to A3, that was just adding multiples of rows. So determinant of A2 should be minus 8 as well. To get from A1 to A2, we scaled one row by -1, so that should be 8. But then to get from A to A1, we swapped rows, so that should give us a minus sign. So our determinant at the end of the day should be minus 8. And you can check this using other methods to compute the determinant, the cofactor expansion, or using a computer algebra software. But this is using row reduction. We row reduced to a triangular matrix and multiply the diagonal elements, and then we traced back to the original value of the determinant. Okay, before we finish up, here are some fun properties of the determinant, how it interacts with multiplication. So if you have a multiplication of two square matrices, let's just say A and B square, then the determinant of the product is the product of the determinants. And this makes sense if you think about matrix multiplication as kind of doing one matrix transformation as after another. So this is matrix transformation B followed by transformation A. Okay, well then that map, B followed by A, first you stretch it however much B stretches it, and then you stretch it again by however much A stretches it by. Okay, if we're thinking about determinant as volume stretching. So it makes sense that that would just be the product of the stretches. So the stretch should be equal to the product of each stretch. Okay, well, what does that mean in terms of the determinant of the inverse matrix? Well, I know that A times A inverse is equal to the identity matrix. This is just the matrix with 1s on the diagonal, so its determinant should just be 1. So this should tell me that the determinant of A times the determinant of A inverse will be equal to the determinant of I by the previous property. So this means that, and we know that this is equal to 1. So that tells me that the determinant of A inverse is equal to 1 over the determinant of A. Okay, which is pretty cool. We have just one more construction left before the end of the lecture, and that's a formula for the inverse matrix using cofactors. So let's define the adjugate matrix first. For A, a square matrix, we define the adjugate of A to be the transpose matrix of the cofactor matrix. Okay, so for example, let's do this in green. If we have A is equal to, if A is 3 by 3, then the adjugate matrix of A corresponds to the transpose of the cofactor matrix. So we'll have, instead of C1, 2 here, we would have C2, 1, C3, 1, C1, 2, C1, 3, C2, 2, C3, 3. And again here, this will be C3, 2. This would be C2, 3. Okay? So all of the cofactors using the formulas we saw before for cofactors, but just you transpose it after the fact. So instead of in the 2, 1 entry having, or rather in the 1, 2 entry having the cofactor corresponding to 1, 2, you have the cofactor corresponding to 2, 1. Okay. So then once you have this adjugate matrix defined, then our formula for the inverse, A inverse, is equal to 1 divided by the determinant of A times the adjugate matrix. Okay. Let's see this in action. So we want to, perhaps a simpler example first. So in a 2 by 2 matrix, we said we want to know what the inverse matrix is here. Well, it's going to be equal to 1 over the determinant times the cofactor matrix transposed. So this should be C11, C21, C12, C22. Okay, well, the determinant we've seen before is AD minus BC. The cofactor, so C11, is the submatrix that we get omitting the first row, first column, so that's going to be D. For C21, we pick up a factor of -1, as well as the entry we get when we omit row 2, column 1. So that's going to be B with a new minus sign here. For C12, it's the entry that's left after deleting row 1, column 2, so that's going to be C, again with a minus sign picked up. And C22, that's the entry we get leaving out row 2, column 2, which is A. And this is the 2 by 2 matrix inverse formula that we saw before. Okay, cool. And this is, we just derived it from this general formula in terms of the adjugate matrix. Okay, and now let's do this for a specific example of a 3 by 3 matrix. So we're looking to use the formula for A inverse as 1 over the determinant times the adjugate. Okay, so to get the determinant of A, so first of all we need the determinant. So let's go ahead and compute it. Determinant of A, let's expand on the first row, so it'll be 1 times this determinant plus -1 times -2 times this determinant. Wait, I definitely did something wrong. Here we go. So determinant. So again, we're going on the first row. So we take 1 times this the determinant of the submatrix you get from omitting first row, first column. Okay, then this one is for second row, first row, second column. And then we'll have +1 times what you get from omitting first row, third column, which will be 2, 1 minus 1, 3. Okay, so this is equal to 1 minus 12 plus 2 times 2 minus -4, or +4, plus 1 times 6 plus 1. So this is -11 plus 12 plus 7, which is 8. Okay, so we have our determinant, and now we just need our adjugate. So for our adjugate, we're just going to compute all of the cofactors. So we've done C11 already. That's going to be -11. C12 is going to be 6. Sorry, it should really be -6 because we want to include the minus sign. And C13 will be 7. Okay. Now we need C21. This is going to be -1 because of we pick up a factor of -1 times this determinant, which is -2, 1, 3, 1. And that is -2 minus 3, which is -5. So this becomes +5. C22 is So we get no factor of -1 because it adds up to 4. And it's this determinant 1, 1, -1, 1, which is 2. Okay? Okay, so we have C21, C22 now, and we need C23. This is equal to -1 times what we get after omitting second row, third column, which is 1 minus 2 minus 1, 3, or 3 minus positive 2, so that's 1. So this is -1. Okay, then we have C31, which is no factor of -1. We get -2, 1, 1, 4, which is -8 minus 1, which is -9. C32 is -1 times, okay, we're omitting third row, second column, so it's 1, 2, 1, 1, 2, 4. And that's 4 minus 2, or 2, and so this is -2. And we're just left with C33, which is equal to 1 minus 2, 2, 1, just 1 minus -4, or 5. Now to use the formula for our inverse matrix, we have A inverse equals 1 over the determinant times the adjugate matrix. So we have 1 over 8. And now as we enter the cofactors we've computed, we enter them according to columns because we have to do the transpose. So we have -11, -6, and 7. 5, 2, -1. And -9, -2, and 5. Okay. And this should be our inverse matrix, and you're very welcome to multiply it with the original matrix and see if what you get is indeed the identity matrix. Until next time, thanks so much for your attention, and I'll see you then.